The significance of facing the Kaaba has prompted a monumental development of mathematics and astronomy in the religion of Islam. As mentioned by David A. King in his book, World Maps for Finding the Direction and Distance to Mecca, for Muslims more than any other religious community in human history, such as the Babylonians, Jews, and Christians, the performance of the most important ritual acts has been assisted by procedures involving astronomy and mathematics. The organization of the lunar calendar, the regulation of the astronomically defined times of prayer, and the determination of the sacred directions toward the sacred Kaaba in Mecca. These are topics of traditional Islamic science still of concern to Muslims today, and each has a history going back close to 1400 years. It is important to note that Muslims developed astronomy by building on the works of Ptolemy as well as Hellenistic, Iranian, and Indian astronomy. As mentioned by King, they were in a position to criticize and improve upon the earlier traditions, and to select what they found most acceptable. He continued on to mention how they developed a distinctly Islamic astronomy, which was without rival from the 9th to 15th century. There has been a numerous number of people who have attempted to determine the direction of the Kaaba during this time. However, we will focus on just a few of those individuals, beginning with Abu Rayhan Muhammad ibn Ahmed Biruni, simply known as al-Biruni. Al-Biruni was born in 973 in Khwarazm, which is in modern-day Uzbekistan. He was a polymath, but we will focus on his contributions made in math, astronomy, and geography for determining the direction of the Kaaba from Ghazna, Afghanistan. Al-Biruni had an inclination that the world was not flat, but rather a sphere, which is highly impressive considering he lived in the 11th century. Although the earth is not exactly a sphere, it is close enough to being one, and thus mathematical calculations can still be used on a sphere as the discrepancies would be negligible. It is important to note that before al-Biruni was a man named Habash al-Hasib, who tabulated the sine, tangent, cotangent, verse sine, and cosecant functions, but also compiled a set of tables of various auxiliary trigonometric functions, so devised that successive applications of them lead to the solution of the standard problems of spherical astronomy. These tables mark a staggering advance over the primitive methods of the Indian tradition, and they have no precedent in the Greek tradition. Inevitably, al-Biruni would benefit from al-Hasib's works. It is obvious to anyone that the shortest distance between two objects A and B within sight of one another is a straight line that connects from A to B. AB can lie anywhere on the globe, but here, let AB lie on the equator. Al-Biruni was able to conclude that, based on the Earth being a sphere, if one were to draw a line backwards from object B, it would eventually meet up behind object A. Thus, this line would go around the world and form a circle that would bisect the Earth in half. This is what was called Da'ira Uzma, or Great Circle. It is called a great circle since it is the biggest circle that can dissect a sphere. The simplest illustration of this is to think of the world being split into two halves at the equator. As mentioned by Nuh Hamim Keller in his book Port in a Storm, a fiqh or Islamic jurisprudence solution to the Qibla of North America, al-Biruni more than 900 years ago calculated with nearly perfect accuracy the Qibla for Ghazna, where the Great Friday Mosque was built by his patron Sultan Mahmud of Ghazna, some 1,933 miles from Mecca in present-day Afghanistan. It was a Muslim discovery that has been the basis for scientific calculation of the Qibla for nearly 1,000 years. Here we can see a diagram of al-Biruni's conclusions, which is taken from Keller's book. Keller mentions in his book, al-Biruni actually discovered 4 different ways to calculate the direction of the Qibla, which he defined in terms of the Great Circle. Because he found it difficult to mathematically prove the shortest path between 2 points on a sphere is along the Great Circle between them, al-Biruni resorted to several spatial constructs to mathematically define the direction of the Qibla from the person praying. It is important to note the role that geography played in al-Biruni's determination of the Qibla. Al-Biruni wrote a book entitled Tahdid Nihayat al-Amakin, the determination of the locations of cities, which was based on mathematical geography. As mentioned by King, indeed, the need to determine the Qibla in different localities inspired much of the Muslim activity in mathematical geography for close to a millennium. In this book, he discusses how he determined the latitudes and longitudes and hence the degrees to face Mecca from Ghazna. He also used spherical trigonometry and projection methods to derive the Qibla. Al-Biruni also provided the latitude and longitude for over 600 locations. The connections between astronomy, mathematics, and geography were vitally important for al-Biruni. For his great accomplishments, al-Biruni is known as one of the greatest Muslim minds. Nasr ad-Din al-Tusi was born in Tus, which is in modern-day Iran, in 1201. At-Tusi's work on determining locations to Mecca has not been studied in depth, so we will not be looking deeply into that aspect of his work. To his credit though, he did compile treatises of his own on theoretical astronomy and rules of spherical trigonometry. However, we will be focusing on a very practical way to determine the direction of the Kaaba from one's location, as At-Tusi determined. At-Tusi determined that when the sun is directly over the Kaaba, all someone would need to do is see which way the shadow is facing and pray in the opposite direction. The sun passing over the Kaaba only happens twice a year, as At-Tusi himself mentioned in Kitab al-Tadhkirah. The sun passes exactly over Mecca when in the 8th degree of Gemini and the 23rd of Cancer at the time of midday there. These days are on May 28th and July 16th. We will return to this method and create a model to demonstrate the implications of this a little later. Shams ad-Din Abu Abdullah al-Khalili was born in 1320 in Damascus, Syria, and he was a timekeeper situated at Damascus's Grand Umayyad Mosque. Many astronomers before him, like al-Biruni and al-Tusi, presented trigonometric tables that showed the result of their findings of the Qibla from various locations. As David A. King mentions in his essay on al-Khalili's Qibla table in the Journal of Near Eastern Studies, al-Khalili had the most sophisticated trigonometric table known to me from the entire medieval period. He had about 40,000 entries, far superior to any other mathematician of his time. As mentioned by King, his most outstanding achievement in computational mathematics was his table displaying the Qibla as a function of geographical latitude and longitude. Here is an example of his Qibla table, which is in King's work but is taken from MS Paris Bibliothèque Nationale. In this diagram, X is one's current location, P is the North Pole, and M is the city of Mecca. Furthermore, the latitude and longitude can be denoted by phi and L at our current city and at Mecca. In this diagram, let Q equal angle MXA, which is called the Inhiraf al-Qibla in Arabic. Thus, in today's notation, his formula would equate to Q is equal to arc cotangent of sine phi cos delta L minus cos phi tan phi at M over sine of delta L. Later on, we will return to a formula that is similar to this. As mentioned by King, the various exact solutions devised by the Muslim scholars are equivalent to this formula. The most common modern-day map comes to us from Gerardus Mercator, who lived in the 16th century. This is his map that we are all used to. With this development, it would seem easy to determine the direction of the Kaaba. All one would need to do is draw a straight line from one's current location towards Mecca. If we tried this from Waterloo, Ontario, it would appear that one needs to face in a southeastern direction to face towards Mecca. Many early mosques in North America would indicate that this is the case as well. In fact, the first mosque built in Canada, Al-Rashid Mosque, which is in Edmonton, was originally oriented towards the southeast. However, it has now been changed from this direction. In the 1960s to 1970s, The majority of mosques in North America change their orientation from the southeast to northeast, thus resulting in thousands of Muslims changing the direction they prayed. But why would this be the case? The first problem when using the Mercator map is that the world is not flat. Furthermore, longitudes are not parallel since they all begin at the North Pole and end at the South Pole. Hence, the Mercator map actually provides a distorted version of the world. By comparing the Mercator map with, say, the Meccan azimuthal projection map, we can easily tell that one would not face southeast on this latter map. Hence, the maps we orient ourselves with are very important, and if not used properly, they can distort the reality of our world.